Now we're going to talk about antiderivatives. That is, we're going to undo derivatives. An antiderivative, capital F, is an antiderivative of f, a function f, and we usually write that as lowercase f, on an interval I if the derivative of capital F of x is equal to little f of x for all x in I. For example, if I say the derivative of x is equal to 1, then an antiderivative of 1 is x, since f prime of x is equal to 1. Since the derivative of x squared is 2x, then I can say an antiderivative of 2x is x squared. Since the derivative with respect to x of sine x is cosine x, I can say an antiderivative of cosine x is sine x. I keep saying an antiderivative, it's because there's an infinite number of them. That is, if I had the derivative of x plus 12, that's still equal to 1. If I had the derivative of x squared plus 3, that's again equal to 2x. So what's going on here? I can talk about a family of antiderivatives. If capital F is an antiderivative of lowercase f on an interval I, then I can write all antiderivatives of f on I having the form f plus c, where c is an arbitrary constant. If I were to graph my f and then my plus c's, I see that I could take my function and I could shift it up and I could shift it down by any arbitrary constant. F doesn't have to be a line. I could let f be a curvy function. And again, if I added any arbitrary number or subtracted any arbitrary number, I still have a family of antiderivatives. Here's some practice with finding antiderivatives. The trick to finding antiderivatives is sort of like the trick of knowing division if you know multiplication. Division is undoing multiplication. Antiderivatives are finding the opposite of derivatives. So what could I take a derivative of and end up with 3x squared? If I have x cubed and I took its derivative, it would get me back to 3x squared. So f of x is an antiderivative of f of x. If I add the plus c, that's my entire family of antiderivatives. Likewise, for part B, I recognize this as inverse tan. If you're not comfortable with your derivatives, you're going to have a hard time finding antiderivatives. So I know that an antiderivative of 1 over 1 plus x squared is tan inverse of x. And if I add my plus c, then I have all the antiderivatives of f. And finally, my part C, I'm going to have negative cosine t, because I know if I take the derivative of cosine t, I get negative sine t. And my little f of t is already positive, so that means I'm going to have to put a negative sign out front. Again, my last step is to remember the plus c. We're going to come up with a new notation for the phrase, find the antiderivatives of f. And that's with an indefinite integral. And I draw this kind of funny little stretched out s thing of f of x dx. This is the indefinite integral of f of x in terms of x. That's what the dx is. Let's look at a very specific example. If I have the integral of x to the p dx, the antiderivative of that is x to the p plus 1 divided by p plus 1. And we have that because if I took the derivative of this, I know I would get p plus 1 times x of p plus 1 minus 1 divided by p plus 1, and that would simplify to simply x to the p power. Again, my antiderivative has to have that plus c to make it the family of antiderivatives. We're going to move this from an example to actually calling this the power rule for indefinite integrals. Let's come up with two other rules that we can always count on. Two other rules we can have are the constant multiple rule and the sum rule. I can pull a constant out of an indefinite integral in the same way that I can pull a constant out of a derivative, and the sum rule is similar to the derivative rule. I can take the individual indefinite integrals of two functions added together. Let's do some examples. Alright, we've got this integral, so I'm going to use the sum rule and I'm going to split this up into three separate integrals. At the same time, I'm pulling that constant 3 out of my first term. I can pull the 2 out of my second term, and I can pull a negative 5 out of my third term. And I rewrite the square root as x to the 1/2 power. Now I'm going to use my power rule. The integral of x to the 5th dx is x to the 5 plus 1, or 6, divided by 6. The integral of dx is simply x. The the integral of x to the 1/2 is x to the 1/2 plus 1 divided by 1/2 plus 1, and I'll remember my plus c. Let's go ahead and simplify this, and now I've gotten it down to my final simplified answer. Here's my next example. Now remember, I did the sum rule. I'm going to write down something you can never do. If you try to do this, you're going to make your Calc 2 professor extremely sad. So what we're going to have to do is break up that fraction into two separate fractions. Once I do that, I can simplify and get it down to this. Now I can go ahead and use the power rule. Remember, the integral of x to the negative 10 is x to the negative 10 plus 1, which is negative 9. Don't make that negative 11. Once I have this, I can simplify and get this for my final answer. Let's do one more. Again, if I have two things multiplied together, I'm not going to be able to break that up into two separate integrations. What I'm going to have to do is multiply that binomial times a binomial. Once I have this multiplied out, I simply use the power rule for integrals. And when I do that and simplify, I get down to this final answer. Let's now look at some trigonometric functions and finding those antiderivatives. My first example, I recognize that as the derivative of tangent x, so I can simply write that this is equal to tan x plus c. Again, if I want to check my work, all I would have to do is take the derivative of tan x plus c, and I would get secant squared x plus 0, which is what I started out with. For my second example, I'm going to split this up into two separate integrals by the sum rule. I'm also pulled out that constant by the constant multiple rule, and then I go ahead and get this. And this simplifies down to x squared plus 3x, x squared plus 3 sine x plus c. Again, if I took the derivative of that, I would get back to what I started with. Let's take sine x over cosine squared x. I don't recognize that as a known derivative, but what I can do is rewrite this. If I rewrite this as such, and then recognize that this is secant x tangent x, and that is simply the derivative of secant x. Let's do another one. Let's do 2 over pi sine x minus 2 cosecant squared x. Again, we're going to break this up into two separate terms and two separate integrals. By now we're comfortable with saying the antiderivative of sine x is negative cosine x. So I'll put that negative sign out there. And when I took its derivative was cosecant squared x, well, that is nothing more than cotangent x. Well, close. I know that the derivative of cotangent x is negative cosecant x, so I'm going to put in a negative sign in front of my cotangent. Again, I need to remember that plus c, and this whole thing simplifies to the following. If I have something like this, again, I'm going to have to break this up into two separate fractions, and when I do that, I see my first term I'm going to have to do a little bit more manipulation. I recognize that cosine x over sine x is cotangent x, and then I have a 1 over sine x left behind, which is secant x. This is very similar to the example I just did. And sine squared x divided by sine squared x is just equal to 1. So what I'm left with is this, 4 times negative cosecant x plus c, or negative 4 cosecant x plus c. You might recognize that all I'm doing at this point is going through a bunch of different examples. It's because all we're doing is taking the derivatives that we know and trying to recognize them as an antiderivative or an indefinite integral. For example, this antiderivative, this indefinite integral, when I take its derivative, is equal to 1 over x. Well, that is simply equal to natural log of x, and we're going to use the absolute value bars. Again, if I took the derivative of natural log of x, I would get 1 over x. So when I see an antiderivative in the form dx over x, I know that it integrates to natural log of x plus c. The question is, the power rule that I did, why doesn't this power rule work for a power to the negative 1? Well, that's because I neglected in my power rule to add a very important fact. When p does not equal negative 1, I need to add that. If I let p equal negative 1, x to the negative 1 plus 1, that would be x to the 0 power, divided by negative 1 plus 1, which would be dividing by 0. That's generally not a good thing to do. So this power rule worked for everything as long as p does not equal negative 1. When p equals negative 1, that's when I'm going to go ahead and say that if p is equal to -1, that's equal to the natural log of the absolute value of x plus c. Let's say I had e to the x divided by 3 dx. The first thing I'm going to do is pull out that constant, and then I'm going to remember that e to the x was one of my favorite derivatives because the derivative of e to the x was just e to the x, which means its antiderivative, or its indefinite integral, is also e to the x. If I see something like this, again, the first thing I'm going to do is break this up into two separate integrals. And the first term I'm going to recognize as inverse sine. I've already discussed the fact that the integral of 1 over x dx is natural log of the absolute value of x. I'll have the 3 out there for the constant, and then plus c. So in addition to knowing our trig, we also need to know our inverse trig. Let's end this with two more examples. For my first one, I'm going to do the same thing I've been doing, breaking this up into two separate integrals. When I do that, I'm going to simplify, and when I do that, I get my final answer, after I included my missing 3 in the denominator for my second term, and this whole thing equals 2/3 times the quantity x squared plus natural log of x plus c. With our next problem, I can't split this up. Again, don't do that, you'll make your Calc 2 professor very upset. But I don't recognize this. So what I'm going to try to do is first of all factor. Well, this looks helpful, and although you might be tempted to do this, please don't, you can't cancel terms. What I'm going to do is a trick. What I did to my numerator is I added a 1 and subtracted a 1. It's because I know this and this now match. Now I can split this up into two separate fractions. Once I do that, I see the first term just divides out to 1. The integral of 1 is simply x, and the integral of 1 over 1 plus x squared, well, that I recognize as tan inverse. And again, I'll have my plus c. The key to figuring out antiderivatives is simply practice, practice, practice. If you don't do the homework, if you don't go through and practice these, you're not going to get used to recognizing antiderivatives.